Okay. Hi, everybody. First, I wanted to say some things about exercise 1. The first thing is that it's due tomorrow. Maybe you haven't noticed, but it says so here. The second thing, okay, so the third question was a little advanced and gives you a glimpse of the topic that we'll cover today. And I got some people asking me about the third section, section C. So, yeah, okay. So first, I want to say this is a little fine point where I said extinction versus stability. In stability, I meant a population that is not zero. So there is a stable population, and it's not zero. Okay. So I'll show something a little analogous with the logistic equation. So in the logistic equation, we had n dot versus n looking like this. You also have this, but of course, all this is a non-physical range of negative populations. And we had two fixed points. And this is the vector field, where this fixed point, let me see if I remember off the top of my head, this was the equation, right? So this fixed point was K. And then you could ask what this looks like for different values of K, right? So as K gets larger and larger, then this part of the curve that has a positive n dot is a larger part. You get to probably larger rates, and we could probably plot something like this on the n versus k plane. I can plot the curve that gives me n dot, we'll call it n dot 2, as a function of k, right? And it should look something like this, right? N dot versus n dot, second n dot just equals k, right? With a straight line, not like I drew it. So I have this curve, and every point on the curve is a fixed point. Okay, it just has a different value of k. Or you could say that every section that I would take out of this plot, okay, like this section here, is a phase portrait. Okay, what I see here is actually I have this. This is n dot n star 2 versus k, and here I have n star 1 as a function of k, but it's always 0. So I have these two lines that mark where the intersections with the n-axis are on the phase portrait. Okay, I could also maybe do a color map where I would have if it's a heat map, I would have red here because between these 2 points I have a positive n dot, and then here I will see the negative in blue. Okay, So each section here represents a phase portrait. Only you don't have the information of the end arm.
What's that vertical line?
This is a section that I take out of this plot, and this section is a phase portrait. Okay.
Oh, meaning take any arbitrary vertical.
Yeah, exactly. Any arbitrary vertical line. And then I can look at this plot as a collection of systems. Okay. This is our system, but we may also be given an initial condition. Okay. So this is a collection of systems. They all have the same R. Okay. I did not play with that here. I could add a dimension, but for now, R will be constant. We have systems with different carrying capacities K and different initial conditions. So this is a system with a certain K, okay, K1, and a certain initial condition N0, 1, okay. And also on the section I took before, I have some K for this section, and I can pick some N0 along this section. And then in the last part of section C, you are asked what is the fate of the different points on this plane? Do they lead to extinction, or do they lead to stability, right? So over here, any point I take will eventually lead me to this fixed point, N star 2. They all lead here. You can imagine all these being phase portraits with the arrows going into this. So here, all of this quadrant, at least, goes to a stable population, which is whose value is given by this line. The carrying capacity, actually.
But how can you get this line by the? Because you drew the dot of between K1 and N0, right?
This one?
Yes.
Or this one?
Both of them.
Both. Yeah, that was.
They are not exactly on the curve. So.
No, they are exactly. They are not on the curve.
Mm-hmm.
So they are not fixed points. They are a certain initial condition, so you can start from any initial condition, and it can be here or here or here or here, just some value of n, okay? This is why I keep this as n and not n star, because here I have different values of n. So these are different initial conditions, and when you start from them, you will probably go into some fixed point. So this, for example, should be this point here. And then this is our phase point, and it flows to here. And on this plot, it looks like this, because K does not change. K is a parameter, so you only go vertically here. So it's another way of looking at the dynamical system, which extends the treatment to different values of the parameter. Okay? And this is what we'll do today. So over here, everything goes into a stable population. And this is the logistic equation, the logistic model of population growth. In your question about the alley effect, some region of the plane might lead to extinction. Okay? And then you, just before this, you are asked which region of the plane behaves like the logistic system. So when I wrote that, I meant qualitatively like the logistic system, in that it only leads to a stable population and it does not have extinction. That is what I meant by equivalent to the logistic system. Okay? Good. So now we will reach these sorts of plots more systematically. So today's topic is bifurcations. And we are going to see them on our one-dimensional systems. But of course, they also occur in two-dimensional and higher dimensional systems. Seeing them in one-dimensional system is most instructive. Okay. So, like we saw with the logistic equation, the behavior of the system might depend on the parameters. Over there, we had the value of the fixed point depending on the parameters. Okay. So, so what I showed you with the logistic equation was just a quantitative change. It's not essential. Okay. It's just the value of the fixed point, but over the whole plane there, all the systems that we could choose would go to a stable population eventually. The more interesting case is when changing a parameter changes the qualitative behavior of a system. Okay, so that means it might change the stability of a fixed point. So a fixed point that for, say, k equals 3 was stable, for k equals 4, it will suddenly be unstable. And then this is a different system. Or fixed points might vanish, or they might appear, so they might exist for certain values of the parameter, and then they might not exist for other values. Okay, so bifurcations occur when fixed points appear or disappear, or fixed points change stability. And when I say they appear, it's not like I have a given system and I let it run, I let it evolve, and suddenly a fixed point disappears. Okay, no, the system is given and its parameters are set. I mean that they appear or disappear as I change one of the parameters of the system. Okay, so the simplest bifurcation we can see in this prototypical system. Okay. Of course, our parameter is real. Our variables are real. I got questions about this in previous years, so just to make sure, you know. So we have this system. It's pretty simple to analyze, but the value of r is important. So we'll start with a negative r. This is just a parabola shifted downwards. Right? It has two fixed points, and by our geometric methods, we already know how to categorize them. One stable, one unstable. And we have the flow in the system. Okay? Is it okay? Too loud?
No. Yours sounded like bells ringing.
Okay. Yeah, I heard something. Okay, so we have two fixed points. Yeah, okay, this is enough. Now, we have a special case when r is just 0. This is a half-stable fixed point. Another thing I wanted to say about the exercise is that you are not required to um, to analyze stability beyond the first derivative. Okay, so here, if I would look for the df over dx, okay, this will be 2x, and when I take it at x star, evaluated at x star, I get 0. So for this kind of case, also in your exercise, we just say that is this requires further analysis, which we won't go into. And according to the geometric method, we know that this is a half-stable fixed point. Yeah?
Every time it's half stable, the first derivative will be 0?
Yes. Yes. But if the first derivative is 0, it doesn't mean it's half stable, okay? When it's half stable? I don't think so, no. No. Here, if you do it again, you get 2. Okay. Okay, so now for a positive r, I also ask you to consider the phase portrait when you don't have any fixed points. Okay, you can have a phase portrait without a fixed point. You still have a vector flow. Okay, if x is negative, it starts growing, becoming less negative, but the rate is getting smaller and smaller until the rate is smallest here, and then it becomes larger. And this is an example of a bottleneck. Okay, we'll see that later. But it means that even if you don't have a fixed point, you might have interesting things like a deceleration in the behavior at some region of the x-axis or of the phase space. But for now, I just ask you to consider also the phase portraits without fixed points and see what happens there. And you could imagine that we are changing r from negative to positive, and this parabola goes up, and then the fixed points, they come together slowly. When r equals 0, they collide, and in fact, they annihilate each other. When r is made to grow from 0, then there is no fixed point. They came close together, they merged and disappeared when r was increased. Okay, and the point is that the dynamics really changed qualitatively, because as long as I was in this range, I could change r and only get changes in the values of fixed points. These are things that we even don't always care about, the exact values of fixed points. Sometimes we cannot find the exact values, and we only care that there is a stable fixed point here and an unstable fixed point here. Okay, so these changes are less important for us. Okay, and the changes that matter are changes like this, when r is already past some critical value, and suddenly we don't have these fixed points. This is a bifurcation. So now we like to see this kind of from a bird's view. and we can plot r on the abscissa and x on the ordinate. Let's do it in blue. Now, I already have the values of the fixed points, right? Plus, minus, negative, square root of the absolute value of r. So I already know that these fixed points appear as curves on this plot. Okay, so this will be x2 star as a function of r, x1 star as a function of r. So now we see what happens to the fixed points as r is changed beyond this critical r, rc, which is 0. We have no fixed points. Another thing that we like to mark on this plot is the stability of fixed points. So the convention is that an unstable fixed point is marked with a dashed line. What we plotted here is called a bifurcation diagram.
Is this the graph of the same function? I mean,
No.
It's dependent. Oh, so what function is?
This?
Yeah.
This.
But it is that function. You're graphing it at.
It's the same system, but I'm not plotting x dot. I'm plotting x star.
Right.
Okay. Okay, the bifurcation that we found here is called a saddle node bifurcation. And the term saddle nodes comes from two-dimensional dynamics, where in this type of bifurcation you always have a node, which we will introduce later, and a saddle colliding and annihilating each other. Here, what we had is stable and unstable fixed point, but the term belongs to the two-dimensional dynamics. Yeah, okay, so in a saddle node bifurcation, the fixed points may merge and cancel each other, or they may kind of appear out of thin air depending on the way you look at it, okay? Or if I had written x dot equals r minus x squared, situation would be opposite, and these curves will be on this side. And as we increase r, we would have two fixed points suddenly appearing and starting to diverge. Okay, now when we deal with bifurcations, we have those prototypical examples that we call the normal forms. Okay, so this is a normal form of a saddle node bifurcation. Okay, and the reason is that if for any function that has this parabolic shape, and when a parameter is changed, it might cross the x-axis. So for any function near the crossing of the x-axis at the critical r, you can approximate it as a parabola. Okay, so any function that has this shape and might cross the x-axis can be approximated by a Taylor expansion to this form. Okay, and I'll do this now. Good. Okay, so most of you probably did not encounter a Taylor expansion in 2 dimensions. Here we are going to expand on the x-axis and also on the r-axis. Okay. No. Okay. And yeah. So what we have here are operators, okay, of the derivative according to x or according to r. And when they are raised by a power, what you do is basically take the second, third, and so on derivative, the nth derivative, okay? And then use it as an operator on the function, and finally evaluate it at the fixed points at the critical value of r, at the bifurcation points. So if I would do it for f of xr equals r plus x squared, I get that I can approximate x dot this way. Okay, so the first term is just the function evaluated at the bifurcation point, okay? Because when this is 0, this whole thing is just 1. And I only get the function evaluated at the bifurcation point. So this is the 0 order term. Now, first order terms is like writing 1 here. So you just open the parentheses and you get x minus x star. Plus r minus rc times the derivative according to r. Now I have second order terms. This is like opening a binomial. So the first term is just this squared, x minus x star squared. And like I said, the derivative taken to the second power will just be a second order derivative. The last term in the expansion is r minus rc squared, with second derivative with respect to r, then evaluated at the bifurcation point. And then they have a mixed term, x minus x star times r minus rc. Okay, and so strictly speaking, I should have here, I have 2 mixed terms actually. So I have dx plus Okay. And then I have third order terms or higher. I hope this was clear. What? Yes. Thanks. Don't. This one? I still need it. Wait. Yeah, I still need it. Hmm? Why? Because it's here. Okay, but no, but they did not group them. Okay. Okay, so let's see what this gives us. The function evaluated at a fixed point is just 0, right? Okay, it's hard to see here, but the derivative here in the saddle node bifurcation, the derivative with respect to x is 0 at the bifurcation point. Okay, the curve is tangent to the x-axis. So this also goes to 0. Okay. What I have next is r minus rc with a derivative of f with respect to r. This is 1. Okay. Right. So this remains. It's a leading term for r. Next, I have this, and yeah, okay. So the second derivative with respect to x, we already mentioned it before, is just 2, right? This is 2. Cancels with this, and I remain with this term. Okay, so let's mark somehow the terms that remain. And so on and so on. These are the leading terms. So when I approximate, I only care about the leading terms. And so finally, I get x dot equals this some constant times a linear term in R and some constant times a quadratic term in x, and so on and so on. These I write these as constants because this might not have been 1, for example. This might not have been exactly 2. Okay? In our case, they were both equal to 1. But the important thing is that here, this is linear in R and quadratic in x. And this is exactly the function that we analyzed before. No. Okay? Yeah. Okay. This thing, so any function that is not this, okay, it might be a complex expression, might be brought to this form around its bifurcation point if it's a saddle node bifurcation. So, and then if we would shift our coordinates and scale r in the correct way, we will get to this thing in the region of the bifurcation point. Okay, and you are asked to do this in exercise 2. Now, this was a system where fixed points could vanish or appear, but once they appear, their stability doesn't change. Now we're going to look at a system where the stability of fixed point changes. So in this type of systems, for example, a system like we saw before with the logistic equation, you have a fixed point like x equals 0 or x equals r existing for any range, for any value of r. We showed this for k, any value of k, we had a fixed point. So the fixed points exist, but they might change their stabilities. So, and the standard mechanism for the change in stabilities is called the transcritical bifurcation. Transcritical bifurcation. Yeah. And the normal form is actually the expansion of this, Rx minus x squared. And this is easy enough for us, right? We already know the system. If we demand that x dot equals 0, we get x star equals 0 and x star equals r. And then we could check what happens for different values of r. So let's start from the positive r for now because we already know it. I just want to remind you of how I plot this kind of function, even if I don't know in advance how it should look like. I look at the region of very small x. So at very small x, x is larger than x squared. So the function behaves like Rx. So it's linear. When x is larger, then x squared is the dominant term, or minus x squared, actually. So farther away from the origin, the function should look like an inverted parabola. Actually, yeah, getting this curvature here. And we have these fixed points and the dynamics that we already saw. We never treated this, but this is just negative flow. So this is for r larger than 0. When r is equal to 0, then we just have x dot equals minus x squared. No, confused. Okay. When r is negative, so I'll use the same method as before. When r is negative, near the origin, Rx wins. It's the dominant term, but r is negative, so this is a negative linear function. And away from the origin, the x squared is dominant, so we have the inverted parabola dominating. So it should look like this. Okay. So now we can imagine that starting from here, as we increase r, this parabola, maybe I can illustrate it. This parabola wanders, okay? It kind of gets lower and lower until at r equals 0, it looks like this. And then as r grows, the parabola shifts its position again and starts having two intersections like here. So it kind of went down and then up. And in the meanwhile, what happened to the fixed points is that they got closer and closer, they merged, but when we increased r further, they did not disappear, they started diverging again, only it looks like they changed the stability. So if the left one was unstable, after it merged with the right one, it remains stable. But I'll show you how this looks in the bifurcation diagram, and you'll see that it looks like as if they switched, as if one gave its stability to the other. So our fixed point is just located at R. So this is pretty easy to plot on the bifurcation diagram. Initially, we had, for negative R, we had a stable fixed point at 0 and an unstable fixed point at R. So this is just the curve x equals R for negative R. Then they met, and for positive R, the fixed point in 0 is unstable, and the fixed point at R is stable. So we could imagine this being a line for the fixed point at 0, and this being a line for the fixed point at R. And so when they met, it looks as if this one gave its stability to this one. And this is why it's called a transcritical bifurcation, because they cross and they exchange their stabilities. Okay, so we looked at two types of bifurcation, and we have one more type of bifurcation that we will learn, and that's the pitchfork bifurcation, and we'll see it after the break. Okay, so we come back at 2 for the other bifurcation. חושב שתזוז קצת.
וגם לא הבנתי איך התחלת לבטל פה דברים. קיצור.
אוקיי, הדבר הראשון, אני פשוט f של x אחד, תמיד f. הדבר השני, אמרתי שהנגזרת ב-x כוכב שיש לנו את ה-x כוכב היחיד.
נכון, זה מה שהראינו קודם, זה מה שלא צריך להמשיך
זה מה שנקרא כן. אז גם זה יתבטל. כן, עכשיו זה לא יתבטל, אבל אני יודע מה הנגזרת ב-r, היא רביעה של f, כי f הוא פשוט r פלוס x בריבוע, אז לגזור לפי r אני מקבל 1. אז זה לא יתבטל, אבל פה נסיבה כקבוע. וזה גם לא יתבטל, הנגזרת השנייה, זה גם קבוע. תתבטל עם החצי פה, נשארתי עם וזהו, ויכולים גם כן.
השאלה למה זה נשאר זו נגזרת הראשונה הרביעית של x בריבוע, לא, אבל זאת הנגזרת הראשונה הנגזרת הראשונה לפי ואז הוסיפה
אז נכון, זה כן, תדעי שזה בפונקציה לוגיסטית תמיד יש שקיבלתם, יכול להיות שזה n שווה 0.
תעשי אבל עושה משהו עם זה, כן. לא עושה את זה, הוא קיבל בזה.
רגע, אתה מציב את
f, כן.
אם אתה מציב ואתה מציב במקום 2x כוכב 2x כוכב
נראה ככה, כן?
למה 2x כוכב 0?
הפונקציה שלך נראית ככה.
כי f ב-x כוכב,
אם את לוקחת את הפרמטר מאוד גבוה, את מגיעה למצבים כאלה.
לא, זה נגזרת
פה היה לך משהו כזה.
זה הנגזרת של נגזרת.
לא.
נראה לי שזה יכול להגיע
כן לקחת בחשבון את האופציה של n שהוא כאילו
לא, את לא צריכה לקחת בחשבון
שוב.
למה זה 0? שלב.
לא, אני חושב שזה 0 בגלל שמציב ב-x כוכב.
נכון.
זהו, בנגזרת של 0.
אני חושב שזה...
לא, אתה מחבר את הנגזרת.
זה לא בדיוק זה לא... פה ההפרעה היא לא פרבולה.
כן, כי יש כאילו מתמטית את ההמשך, אז מה שמתאר
אז בגלל זה כתבתי equivalency ולא כתבתי...
אוקיי, אבל כשאני מסתכלת מבחינת בגרף שלי, השטחים זה אותו שטח, הוא לא פשוט. כאילו, אנחנו צריכים לתאר אז האזורים בגרף שיתנו כזה דבר, מה שייתן את הדבר הזה, זה מה שייתן לי פונקציה לוגיסטית, וזה גם מה שייתן מצב של לא אקסטינקשן, אלא של סטביליזיישן.
לא, גם במצב שהוא לא אקוויוולנטי לפונקציה לוגיסטית, גם במצב הזה יש טווחים של n שלא יתקיימו בהפרדה.
במצב הזה,
אפשרית הפרדה, אפשרית הפרדה בעצם מבקש לצייר על n מול r, לצייר איזה גבול בין תנאי התחלה שמובילים להכחדה ותנאי התחלה שמובילים
למה כמו שזה
לפי כאילו ה-n דוט versus n שאני יודעת שבטווח בין נגיד שתי הנקודות זה יוביל אותי ליציבות.
נכון, כן. אז אפשר לראות פה.
הוא הסביר משהו שהיא מהשקה.
אני חושב שזה בדיוק הנקודת השקה, כי בנקודת השקה
נכון.
רגע, אבל למה זה נקודת השקה?
כי ככה זה מה שהוא אמר, זה מה שמאופיין את הסאדל
גם מעבר.
שבנקודת השקה
זה שכאן זה n versus n דוט, נכון?
כן,
נכון.
אז יכולה להגיד לי, כל זה מוביל לפה, כל זה מוביל להכחדה.
והנקודה האחרונה שיש לך פה,
באפליקיישן דיאגרם.
יש לך את הפרבולה ואז הנגזרת הראשונה היא אפס בנקודה של
נקודת ההשקה, זה מה שהוא אמר גם שאין מה לחקור יותר.
כאילו,
בתקביל זה היה מה שעשינו בתחילת השיעור זה שונה ממה שרגיל. בתחילת השיעור הוא פרטי K, כי הוא באמת משנה את האלה. של הפיקס פוינט.
זה אחד בגלל שהנגזרת היא אחד.
ביקשתי עבור F, עבור R,
זה משנה אם עשיתי מי והקר לפי ה-Y?
זה תלוי באר
שאין רק ב-Y?
פה אתה גוזר פעמיים שתיים.
נכון, זה פעמיים
אבל אם אתה גוזר פעמיים לפי R זה אמור להיות אפס. אז כל הדבר הזה אמור להיות אפס.
אם אני יודעת שיש שלושה צדדים, יש אחד שתמיד לא המשיך. לא המשיך נורא קצרות שיש לנו כוכב אחד שתמיד לא המשיך. בכל R, אם הוא... אז יש מקרים שבהם יש...
אם אתה פותח את הראשון,
אבל זה נראה לי הגיוני לא הבנתי כל כך
אבל אם הוא מאפס עד אינסוף.
בעצם המטרה היא לא לעשות גרף בכל R, לעשות גרף בכל מחיר כזה של נגיד עקומה לכל
משהו הזה, משהו בריבוע, משהו שונה בריבוע, שתיים זה כזה, זה איפה השתיים, זה מה שקרה.
זה פה, הוא לא פיתח.
שאומרים אין מול R. זהו,
זה מה שהוא עשה.
אבל אז אנחנו נמשיך את זה.
לא, הוא אמר שמשמעית זה רק...
אבל מה עוד נשאר? מה עוד יכול להיות?
כשכותבים ככה, תמיד Y מול X.
כאילו בשביל אני לא מבין איך זה נפתח.
כאילו זה גם לפי R וגם לפי S. כאילו הראשונה לפי R והשנייה לפי
אחר כך בגרף השני. המטרה היא בעצם לקחת את הגרף הראשון ולהשאיר עליו
זה לך שתיים כי אתה לא יכול לחבר פעם אחת פעם. כי אתה כופל את זה לפי זה, כאילו זה לפני זה, ובפעם השנייה זה לפני זה. תחשוב על זה. הרי זה ועוד זה.
שניהם כאילו נגזרת שנייה.
אני כותבת עם...
למה שניהם נגזרת שנייה? כשפותח משהו בריבוע
זה הריבוע זה
כשפותח משהו בריבוע זה A ועוד B בריבוע, אז זה עם השתיים, ואז השתיים זה לא בריבוע. A ו-B לא בריבוע.
ואז D זה D לא יודע.
אוקיי.
אני יודעת שכן.
ואז הוא עושה את זה.
זה היה תרגיל לעשות
תודה.
כאילו אתה סובר שהם לא אפשר כאילו זה אין שתיים.
הגשתי.
בפעם שעברה שלקחת את
למה היא כוכב?
זה מה שצריך לדעת.
למה היא כוכב?
זה מה שצריך לדעת. ה-fix point ב-0 היא הופכת ל-1 ואז למעלה עם זה, אפשר לקרב אותה בטיילור.
את הביפורקציה שלה,
אם הבנתי נכון, זה
מה שבסגנון של צדל, הביפורקציה נמצאת ב-0.
זה מה שצריך בדייל.
זה נכון המשפט הזה? בכל המערכות שיש את הצדל הזה, אז הביפורקציה תהיה ב-0?
לא, ב-X כוכב.
ב-X כוכב שזה...
שבו F שווה... X כוכב לא תמיד יש.
אז למה זה תמיד 0? כי אני
זה
גוזר
רק
לשתי...
במקרה שלנו.
רק לצדל נוד. רק לצדל נוד.
כשאני גוזר לשתי X, נכון? ואז אני מציב X כוכב, למה שזה יהיה 0? כאילו, לא הבנתי.
מציב X כוכב, ואתה מציב, כן, לא רק שאתה מציב X כוכב,
אבל רק אם X כוכב הוא 0 שזה...
כן, פה יצא לך שני X. אוקיי, כן, לא, פה גם יצא לך שזה תופס 0, אבל העניין הוא שבסלולר באפליקיישן, תמיד בנקודת הביפורקציה, זה נראה ככה. ופה זה יצא לך, אני עובר בשני X, ואז בנקודה שבאמת ההשקה קורה, אז X שווה 0. ואז נגזר את זה. אבל בסלולר באפליקיישן זה תמיד טוב. הנגזרת לא תמיד תהיה שני X. הנגזרת צריכה להיות איזשהו ביטוי, אבל להשתתף
נקודת הביפורקציה תהיה ב-X שווה?
לא.
מכיוון שזאת נקודת מקסימום
מינימום. בדיוק, זה תמיד מינימום מקסימום מקומי. אז הנגזרת לא תמיד תהיה שני X, הנגזרת תהיה איזשהו ביטוי שהוא מתאפס פה.
רגע, שזה תמיד ישיק בנקודת
כן, בנקודת הביפורקציה, כש-R שווה RC, אז יש לך את ההשקה עם ציר X, וההשקה קורה ב-X כוכב.
ההשקה קורה ב-X כוכב, זה אומר שבהכרח הנגזרת של הדבר הזה תהיה 0 בנקודה הזאת של הביפורקציה של X כוכב. X כוכב זה נקודת הביפורקציה.
X כוכב זה RC. יכול להיות X כוכב כפונקציה של R, ואז כשאתה מוסיף RC תקבל את נקודת השבט ונקודת הביפורקציה.
המשמעות היא שהנגזרת הראשונה היא לפי X והשנייה היא לפי R.
לא, הראשונה לפי R.
ודרך לפתוח את זה היא פשוט
ליצור כפל לא נכון.
פשוט לגזור את הפונקציה פעם אחת ולהוסיף
רגע, אם אתה גוזר לפי R ב-1 נגיד, ואז אפשר לגזור לפי X זה 0. וגם פה. אם אתה גוזר לפי משתנה 1, ואז אתה גוזר לפי משתנה 1. לא, אם שני משתנים. אתה גוזר לפי משתנה 1, זה נעלם.
Okay, the next bifurcation type is characteristic for systems that have symmetry in them. I'll show you as we go on. I'll show you where the symmetry comes into play. Okay, so we start. I'm going to show the pitchfork bifurcation. And specifically, this one is a supercritical. I'll show you what this means. Pitchfork bifurcation. Its normal form is this. Okay. If you start to analyze the system, then you could start by plotting the function. You could start by looking for fixed points. I'll try to look for fixed points right now. Okay. So first, I will rewrite this. Already, I have one fixed point that always exists. Equals 0. And here, I could break this down into this. This is square root of the absolute value of r. And so I have two more fixed points that exist for r, for positive r. Okay, or r equals 0, but then they are degenerate with this one. Okay, so I have here three fixed points, and I would like to try and plot the phase portraits for the different ranges of r. And for this, I'll use the same rules I used before. I'll start from the simplest case. I draw it in the middle. R equals 0. So this is just minus x to the third. As promised, I have this fixed point, and it's stable. If I try to analyze the stability, I'll get a 0 first derivative, and then I will just say that by the geometric method, I see that this is a stable fixed point. Okay? Don't need to go further. This is why the geometric methods are so useful. I'll just remark that what we have in this case for r equals 0 is not an exponential decay. We discussed this previously. The decay to this fixed point will not be exponential. It will go like t, right? T to the minus half. Okay? To the minus, yeah, no. I think t to the minus 2. So if you would try to integrate dx over dt equals minus x to the third, right, you will get dx over x to the third, and you'll have to integrate over this, and 0 over dt, and then this thing goes like x squared, right? And then when you take this out, when you solve for x, you will get something like this. So this is a slower decay than the exponential decay. Okay? Because the exponent is always the fastest function. Okay. I just made a remark that here, this is not the same decay as you have, for example, in this case. Okay? This is an exponential decay. This decay is not exponential, it's slower. Okay? And I wanted to explain this because by showing you that if you try to solve this differential equation, then you get 1 over x squared is proportional to t. And then when you try to solve for x, oh yeah, it is minus 1/2. You will get this. When you try to solve for x, t will be in the denominator, and it will be inside a square root. But this is just a side note. Right, this was simple enough. Okay. Now, if I ask what happens when r is positive, then close to the origin, the linear term dominates. This goes like rx, and r is positive. Farther away from the origin, minus x to the third is the dominant function. So it behaves similarly to this one, which was just minus x to the third. So the presence of rx mattered for the small values of x. Okay? Okay. So already I see that for positive r, I did get 3 fixed points, like my analysis showed. R equals 0. And for a negative r, near the origin, the linear term dominates, only now it's a negative slope. So I have a negative slope here, okay? And farther away from the origin, this behaves like minus x to the third. So again, I have a positive, I have a stable fixed point. Only now the decay is not slow like here. Here the slope of this curve was 0. Here. This is why the decay was slow. Here the slope is not 0, and the decay is an exponential type decay. Okay. Yes? What? What? You didn't get my explanation of the decays?
Yes.
Okay. So here the slope of the curve is 0.
Right.
So you can imagine that these arrows marking the rate of the decay become smaller and smaller as you go into the fixed point. Okay, so they are very minute. Okay, and
What's the difference to when
to here,
yes.
Because here the arrows decelerate, I would say faster. So here near the fixed point here, you have a very small rate of going into the fixed point. Here near the fixed point, the rate will be larger. Okay, so it will go even faster into the fixed point. So if you plot them, if you plot the solutions, okay? So this is t and this is x, right? The idea is that an exponential decay would go like this, but the other type of decay will be slower. Yeah. Okay, exponential. It's just, you can plot it. This is very crude. But basically, the exponential decay should be under any other function that you write. Right. So I saw the three cases. They match my analysis. And now I'd like to do the bifurcation diagram.
I just want to clarify, the reason why you choose R as 0 less than 0 or greater than 0, so do you always choose R as those three things, or does it
No.
depend on the...
In the normal form, yes. This is a normal form.
Okay, so what are the... If it's not in the normal form, so what values of R are you looking for?
You are looking for values of R that would first, they might give you different numbers of fixed points. So there might be a value of R that dictates that there are 2 fixed points in the system, and then another value of R that dictates 4 fixed points in the system. And then you are looking for the value of R that's critical, where 2 becomes 4.
So how do you go about finding which R that is?
Well, you could do it from the equation, okay?
Mm-hmm.
And you might be able to see it in the plot. Yeah, for example, if I would, if you would have something like square root of x squared minus, if, for example, you might get this, okay? Now this is, of course, this might be another parameter, but here it's set to 10. But here R would, might also depend on x. But the idea is that you might have values of R that give you something that you cannot take the root of. So then, if you have these values of R, you don't have this root. Yeah, actually, I shouldn't have done this. Right. Okay, so when R is negative, is these roots of the equation are complex. Okay, so or imaginary. So you don't have a fixed point with this value because x is real. Okay. Okay. So the bifurcation diagram for this type of bifurcation. For negative R, I only had one stable fixed point. And for positive R, this fixed point at 0 is unstable. And on both sides, I have a stable fixed points. And they go like square roots of R. see why this is called a pitchfork bifurcation. It looks like a pitchfork. You could also call it a trident, but that's not a term that's used. And it's called supercritical because, okay, the critical value of R is 0, right? And above the critical value of R, you get more fixed points. Okay? So this is the supercritical.
What do you mean that you get more fixed points?
Here you had 1, and here you have 3.
Oh, where did these came from?
Where did they come from? From here. It's these two. It's like this curve. As you change R, it flattens here, and then it starts like doing this. Okay?
So it's 3.
Yeah. From 1, you get 3. 1, 2, 3. Maybe you don't see it. There is a dashed line on the R axis.
Oh.
Okay. Yeah, so it's supercritical because the additional fixed points exist for R that is larger than the critical value. That's supercritical.
Is there usually only one critical value? Can there be more than one?
There can be more than one. We'll see this shortly. Okay. You can have multiple pitchfork bifurcation. You know, this could get another pitchfork, and this one. I mean, many things can happen. But we are dealing with the most simple forms now. So we only have one bifurcation in this system. And okay, so the counterpart of the supercritical pitchfork, supercritical, just so this will remain labeled, bifurcation. The counterpart is the subcritical bifurcation, and this happens when the cubic term is destabilizing. Okay, so previously we had minus x to the third. So when x would become very large, x dot would become smaller. Okay, if x would be very positive, x dot would be very negative and bring us back to the small x range. Here, you have a positive factor before x cubed. So as x grows, x dot grows, and this is a positive feedback mechanism that causes x to diverge. It's destabilizing the system. So I'll draw quickly the phase portraits. It's just a mirror image of what we had before. Okay, and you can see that our linear term saves us from the complete destabilization in the vicinity of 0. Okay, when r is small, when r is negative. And if I plot the bifurcation diagram, r and x, I plot this very near the r-axis so you can see. And this is subcritical pitchfork bifurcation. And I'd like to remark that the category of sub or supercritical doesn't have to do with the stabilities. Okay? So this one could also be could also look like this. The stabilities don't matter for whether it's subcritical or supercritical. What matters is the value of r, where the additional fixed points exist. Also, this subcritical it could look like this. Yeah. Yeah. I mean, you could just write here minus r, and then you would flip the image, right? So it might be a little arbitrary. Okay. So for such systems, okay. So I was about to give an example for such a system. I'd just like to say something about this. First, just to state again that, see, for a positive value of r, the system has no stable fixed point, just go to infinity. For negative values of r, if you are here, then you can stabilize, but if you go beyond these lines, then you just destabilize. Now, real physical systems usually don't behave like this, okay? Usually they have higher order terms that will stabilize them. They will come into play in the large values of x, okay? And I'll you'll see them in a moment. Where is the eraser? Okay. Okay, before I show you the higher order terms, I would like to say that we are dealing with a system that is symmetric, okay? And by symmetric, I mean that the function of minus x, okay, this f of x, okay, f of x equals, as usual, this x dot. If you flip x, you flip f of x, okay? So why do I say this is symmetric? Usually this is not symmetric, right? Usually this is the definition of anti-symmetric. Because this is not the f of x is not x of t. If f of x is anti-symmetric, then x of t will be symmetric because you do here an integration to get at x. So it's similar to the way that x squared is symmetric, but its derivative. I'm sorry. Its derivative is asymmetric or anti-symmetric. I think anti-symmetric. So the system that gives you the pitchfork bifurcation has an antisymmetric expression, but when you integrate it over time, you are in a symmetric system. Okay, and so to keep the symmetry, your next term should be the next odd term, the next odd power. Okay, because if you integrate over x to the fourth, you will get x to the fifth. Okay, and that's already, it's not symmetric. If you want to preserve the symmetry, you need odd powers here. Because they want it to be stabilizing.
That's the higher, okay.
Yeah, this is the high, and if this would be plus, then in the physical system there should be some minus x to the 7. Okay, which means, okay, you'll see the bifurcation diagram for this. So here, near the origin, near the x equals 0, you have a subcritical bifurcation like we did before, but when x becomes larger, then the fifth order term comes into play, and you get these curves. So in such a system, if you are at positive r, and you stray away from x equals 0, you will stabilize on another state. Okay? And those of you who came here to study neuroscience will see this a lot. If you look into models of neurons and neural networks, and a lot of times, by the way, I'll just remark that these are saddle node bifurcations here. A lot of times, you see that you have some parameter like an external input, and if you look at, say, the firing rate, you see that when the external input is very low, you are in a quiet state of the cell. You have near zero firing, and at a certain point, you get an opening of another state of a tonic state, but they are still they can still coexist. You can switch the cell or the network from one to the other. This is actually this situation. And beyond a certain point, the quiescent state also becomes unstable, and you can only be in the tonic state. So you have quiescent, bistable, and tonic. And this is a subsection of this. Okay, only in the cell or neural network system, we don't have all this range because you can't have a negative firing rate, for example. Yeah.
I don't understand how this is a function. Two values.
Say again?
If this curve is
How this is a function?
not a function.
Right. I didn't say it needs to be a function.
What is it?
What? It's a relation, but you'll see in a.
What's happening
Let's see.
when x in a point that is above this curve that you
Here.
yes.
You go back here. Okay. So I'll get to this later, but a lot of times you cannot write the function x star as a function of r. A lot of times this is something that you cannot solve analytically. But you can write r as a function of x star. And then you can plot this. Okay, so sometimes this will be a function, but this not. Okay. Right. We don't have a lot of time. Um, okay, so in this system, I'd like you to note how x equals 0, the origin, is stable. In this range and in this range, it's stable, but only if you consider small perturbations. So if you are here and you perturb a little, you will go back. But if you have a large perturbation, then you will go to this state. Okay, so this, so if at this range the origin is globally stable, here it's locally stable. Okay. And another important point that that is seen in this type of system, and I'm not showing this as something theoretical. We'll also see applied models, especially in your exercise 2, where this comes into play. This system is called, sorry, it has a phenomenon called hysteresis. And let's consider this on this plot I made here. It will be more easy to understand. If I have a neuron that has a low external input, okay, and it is quiet, okay, it's probably under inhibition, and so now it's not firing. And as I increase the external input, I inject currents into this neuron, then it stays quiet until a point here, okay, where, or actually it was here, but for the demonstration here, if I inject enough current to this neuron, I will be able to bring it to this state, okay? Now I can, but okay, let's consider the system without my own intervention of injecting current. Let's say that I only increase the external input. I increase, and beyond this point, I give it a very high. I let it. I put it under a very high external input. The neuron can no longer be quiet. It must be here. Okay. So if I'll draw this in red. I took the neuron artificially beyond this point, and then it had to go here. If there is no noise, yes, right. This depends on noise. Okay, let's say that the neuron is all the time perturbed a little. Okay. I took it to a high external input. It must be here. Okay. Then I lower the external input again. Okay. So the neuron rides on this curve here until the external input is too small to support it, and then it will go back to the quiescent state. Now, consider the situation where the neuron has this external input E1, okay? When I started, the neuron was quiet at this situation. But I came back to the situation, and then the neuron was not quiet. And this is because we did this path. Okay? So for the same parameter, the same value of this parameter E, I could be at two different states depending on what I did before. Okay? And this is hysteresis. So the hysteretic systems are not ignorant or indifferent to their history. Although the word does not come from the word history.
But really what matters is the initial time it's not dependent on the path so much as if you inject a current in and the neuron is firing this much, so then it will move based on that starting point.
Wait a minute. Oh, yeah, so this is why I said I'm not injecting current. I'm just controlling this parameter E. Okay? At this point, yes. If I am here and inject a lot of current, I can get here. Yes. But let's say I did not do this. This is another intervention. I'm saying my only intervention is controlling E. Okay? So and like they said, having small noise. That means I can perturb out of an unstable fixed point. Okay, so I just change E, so I'm stable here. If I change it to this value, this is unstable, and I go up there. And then I go back to this value. So there was no injection of current. Okay, there was some noise, maybe a very small injection of current. Okay. Okay, I'll show one more thing. An example, actually. I'm going to show an example of a system with a pitchfork bifurcation. Okay, I pretty much designed the system to show some point. Okay, I have here a linear term, and I have here a term that has an exponent. And first of all, I don't know in advance how to plot this function, and I cannot solve analytically for fixed points because I have an exponential function here. So this is a transcendental equation, and I cannot solve for x analytically. But what I can do, and we've seen this before, I can designate f1 and f2 and plot them both and see where they intersect. So the first one, this linear function, intersects the ordinates at 1/2 and has a slope of 1/2. This is my linear function. The second function, well, its shape will depend on beta. This is a sigmoid, okay? And at very negative values, it is just 0. At very positive values, it is just 1. Okay, it has an asymptote, not to scale. So if beta, so the different values of beta can give me different shapes, but for now, I will say that it can appear as something like this. And then if I try to plot the phase portrait, so here I will have some intersection. I will have some intersection here and some intersection here. And the function is f1 minus f2. That's the linear term minus the sigmoid term. So it should look something like this. Okay, you can see how this will give us a pitchfork bifurcation. If I do this for different values of beta, the slope of the sigmoid will change, and I might get a situation that looks like this, with the line and the sigmoid only intersecting at one point. Okay? Now, I can ask, what is the critical value of beta? And this is for your question from before. Okay? So, the transition occurs when the slopes here are equal, right? If the slope of the sigmoid is equal to the slope of the line, or smaller than it, then I only have one intersection. If the slope of the sigmoid is higher than the slope of the line, I have two intersections. So what is the slope of the sigmoid at 0? I'm looking for f2 prime.
Sorry, could you repeat the thing about the slopes? Shouldn't it just depend on the point where they intersect?
Yes. So this sigmoid, okay, you can see that if here it has a slope that is larger than 1/2, then it must also intersect here and here.
Okay, but if it's less than 1/2, it goes up to the line, but it doesn't.
If it's less than 1/2, the sigmoid is so shallow.
It doesn't touch the line.
It doesn't touch the line except here, and here it's also shallow, and it's above the line always. So I'm looking for f2 prime. I need to differentiate this with respect to x. What you get if you do this, you can solve this at home. Is this, and if I try to evaluate it at x star equals 0, I get beta over 4. So my condition is beta over 4, beta critical over 4 equals 1/2, and therefore critical beta equals 2. And from this, I would go on and plot my bifurcation diagram. And since I found that above beta equals 2, I have 3 fixed points. I mean, I would do it more carefully. I would try to do the phase portraits for all the cases. And this is what you will do also in your exercises. I would do the phase portrait for beta equals 2 and beta smaller than 2, and then see how to plot this. Okay, see that I really do get an unstable fixed point. So this is my my bifurcation diagram. Okay, so we will stop here, and in the next lesson, I will show how I get this quantitatively, like you asked. How is this a function? So this is not a function, but I will actually try to get beta as a function of x, and then plot it. So I might have like a parabola and a condition for a vertical line, and you'll see how this comes out. Okay, and then in the next lesson, we're going to devote most of the lesson to an applied model. It will be very interesting, I think. And we'll give more intuition about these things.
למה כשאתה משווה את השיפועים, אז הוא לא ייגע בקו אף פעם?
רק פעם אחת.
רק פעם אחת? איפה? בנקודת דיפרוקציה?
כן. לא, זה לא נקודת דיפרוקציה. זה נקודת שבט אחת, יחידה.
אוקיי, שבט.
אז יש לי את הקו, יש לי את הסימפטות של הסיגמויד, נכון? זה יכול להיות סיגמויד שזה הקו.
שהוא יהיה אבל שיפוע פה
קצת יותר גבוה מהשיפוע של הקדמון.
לא, כאילו, לא יודע למה זה כבר שאפשר לסתם, כן,
כן.
אוקיי, זה הבנתי. ולמה תכנן
זה מגניב, אבל גם רגע, פרשנות